next talk is on snarks from LWE by non-black box reductions by Zhengzhong, Mingxi, and Bo. And Bo will give the talk.
Okay, thank you for the introduction. Today I'm here to present our work, snarks for EFUP from LWE via non-black box reductions. And this is joint work with Zhenzhong Jing and Mingqi Lu. And first, let me get over this background again. Succinct non-interactive arguments, or snarks, is a protocol between a prover and a verifier in the CRS model, where the prover tries to convince the verifier that some instance X is inside the language L by sending a single round of message. And let W be the MP witness, which we hope that the prover really has. And the succinctness requires that the proof size is much smaller than the MP witness size. And moreover, we require completeness, which means if X is indeed in the language L, then the honestly generated proof should be always accepted. We also require soundness, which means for any instance that is not in the language, and for any efficient adversary, the cheating proof should be rejected by the verifier. And so can we build snarks for any MP language? Starting from the seminal work of Mikali, there's a huge line of work that constructs snarks for MP, and some of them are even efficient enough for practice. However, as we already know, most of them are either in the random oracle model or rely on knowledge type assumptions. And we ask this question again, can we construct snarks for MP from standard assumptions? On the positive side, we do know how to construct snarks for all of MP from somewhat standard assumptions in a series of work. In the work of Sahai and Waters, they built snarks for MP from I/O, which was later constructed from well-founded assumptions. And in more recent works, there are alternatives using two-round laconic arguments, or as we recently heard about, low norms new style and stats conjecture, or proof complexity conjecture. So it remains to ask if we can build snarks for all of MP from more standard cryptographic assumptions, such as learning with errors. And in this region, where we really only want to use really standard assumptions, we know how to build snarks for only some subclasses of MP, such as bounded depth computation, or of P, or batch MP, where the prover tries to convince the verifier that a batch of MP statements are true. And more recently, we know how to build snarks for MP languages whose non-membership has a polynomial size extended Frege proof. However, notably, here the supported languages are contained in co-MP. So can we go beyond co-MP? And this is our first question. Can we base snarks on simple standard assumptions, such as LWE, for a larger class of languages than MP intersect co-MP? And in this work, we further consider a stronger notion of soundness, which is knowledge soundness, non-adaptive version, which has many applications. Intuitively, knowledge soundness requires that if a prover can convince the verifier, then the prover must know a witness. And more formally, in our work, we formalize it as this type of knowledge soundness. There exists an extractor, which is a uniform algorithm that only takes the instance X as its input. And for every adversary that makes the verifier accept, regardless of whether X is true or false, the extractor can query the adversary as a black box by sending a different CRS and observing the cheating proof. And then finally, it should output a witness for this instance X. So this whole extraction procedure is like rewinding the interactive proof setting, but here we only have 2 rounds, so it can only send different CRS and observe the output. So another question is, can we construct snarks with a K from standard assumptions? And unfortunately, there are impossibility results. It is known that snarks with a K for MP are impossible with black box extraction. And the proof idea is to construct an MP instance where there are many different witnesses. Then an adversary can use a different witness to answer different CRS, and the extractor would have really a hard time to combine them to get a consistent witness. But this impossibility result crucially relies on the instance have many NP witnesses. So if we restrict ourselves to UP where the witness is unique, then the impossibility no longer holds. And in this setting, we do know how to construct snarks with a K from IO or evasive LWE. And it remains to see if we can reduce the assumption to standard LWE. So in this work, we also asked the following second question: can we construct snarks with a K for UP from LWE? And here's our result. We construct the first snark with a K for LWE for EFUP with a weaker soundness. I will explain about the weaker soundness in a moment. And EFUP is the UP languages whose witness uniqueness can be proven in poly-size extended Frege proofs. And I'll have to explain extended Frege proofs here again. It's a type of propositional proof system where the proof of a formula phi consists of many lines. Each line is a Boolean formula, and the ith line have two possibilities. Either it's come from an inference rule, where there are some previous lines that can derive this line via a constant size tautology, or it could be an extension rule that defines a new variable like e equals x and y. And the final line should be the theorem statement itself. And notably, extended Frege proof system can express an expression like Cx equals 0, where C is a fixed circuit and X is arbitrary input. So in this work, we consider EFUP, which formally means languages where for every instance X, there exists a poly-size EF proof of witness uniqueness. And witness uniqueness here we formalize as if there are two valid witnesses, then they should be equal. And here we allow the EF proof to depend non-uniformly on the instance X. And intuitively, it means EFUP means the UP languages that you know why it is in UP via EF proofs. Okay, and recall that our result is snarks from LWE for EFUP with knowledge soundness for true instances and a weaker soundness for false instances. And here's the formal definition of the weaker soundness, but it's too complex. I'm not going to go over it here. I'm going to show you a picture that explains it more intuitively. So we get this weaker soundness via a non-black box reduction from an either-or argument. So either we set the CRS size to be lambda, and if it's already sound, then we are done. If it's not already sound, then there must exist a sequence of adversaries, and we will somehow encrypt this sequence of adversaries into the CRS, and then we will somehow prove that with this extended length of CRS, our snark would be sound. Also, if you don't care about knowledge soundness, then we can also state our result as the following, where we only require false instances to have poly-size of EF proofs of witness uniqueness, and we get snarks. We can compare this intermediate result with previous work, the JKLV. In JKLV, they require poly-extended Frege proofs of non-membership, which directly puts it inside NP intersect co-NP. But here, we only require EF proof of witness uniqueness, which we can show a candidate language that most likely would not be in co-NP. So we extend the applicable languages with the caveat of having a weaker soundness. So that basically explains our results. And next, I'm going to the technical overview. So some super high-level overview. We first get our intermediate result 1, which is snarks with knowledge soundness for true instances, but absolutely no soundness for false instances. Then based on this intermediate result 1, we do a non-black box reduction to get our intermediate result 2, which is snarks with weaker soundness for false instances. And the intermediate result 1 can actually be easily derived from JKLV. So I'm not going to explain it in details here. We will focus on intermediate result 2 in the following slides. So let's assume now that we already have a snark that has knowledge soundness for true instances. And let's assume that this snark does not have soundness, which means there's an adversary that makes the snark verifier accept X. Recall that knowledge soundness requires there exists an extractor that if X is a true instance, then the extractor extracts a valid witness. And here the crucial observation is that if X is not in L, then the code of the adversary is an co-MP certificate for X not in L. So it's like this. The co-MP verifier first checks if the adversary makes the snark verifier accept. And if so, it runs the extractor to try to get a witness. And then it verifies that the witness is not a valid witness. And since if X is in L, the witness should be a valid witness, it proves that X is actually not in L. And here we have a proof of non-membership. The idea is to apply the JKLV snark, which is sound for MP languages that have wholly EF proofs of non-membership. And the only difficulty here is to put this co-MP certificate, this proof, into EF proofs. However, it happens that this is unlikely because we crucially rely on knowledge soundness. And knowledge soundness is computational, so it's unlikely that it can be formalized in EF proofs. And our solution to this problem is to define a new logical proof system named cryptographic EF, which extends the standard EF proof system by enabling cryptographic indistinguishability style reasoning. We then extend the JKLV snark by proving that the snark is sound for any MP languages with poly-sized crypto-EF proof of non-membership. And also, this also means that if we can show there exists poly-sized crypto-EF proof of non-membership for all of MP, then we can get snarks for all of MP. And this is actually possible because crypto-EF proofs need not to be in co-MP. This is inspired by and extend JKLM and JJMP. Under this lens, JKLM assumes witness encryption for MP and then use witness encryption to construct this crypto-EF proof of non-membership. If we can change the assumption from witness encryption to LWE, then we get snarks for MP from LWE. Okay, and some future works. First, maybe we could get snarks for all UP from LWE, which requires removing the EF proof requirements, which sounds a bit hard. Or maybe we could get snarks with standard soundness for EF-UP, which requires finding a way to compress the adversary. And finally, maybe we could just prove that MP has poly-sized crypto-EF proof of non-membership, then we get snark for all of MP. And that's my talk. Thank you for listening.
Can you say a few more words about the meaning of crypto-EF?
Yeah. So crypto-EF has all of EF, but we also introduced some random variables that can follow some distribution. And we add a rule that is if a set of random variable follows some distribution D1, and D1 is indistinguishable with D2, then we can directly change the distribution into D2. Yeah, so it enables indistinguishability style reasoning.
Yeah, I'm not sure this question makes sense, but you mentioned in the construction, there's either or, where if you don't have soundness, then you can use adversaries to get a proof of no membership. Does that make the construction non-explicit, or can you make it? Is it possible to make it explicit?
Sorry, make what explicit?
The construction itself of the snark response.
It
seems to depend on like.
Yeah. So the construction is explicit. Let's go back here. Yeah, so here it seems that we need to encrypt the adversary into the CRS, but actually we view the CRS as an FHE encryption. So in construction, the CRS only needs to be random, and only in the security reduction, we would change it into an encryption of the adversary. Yes, so the construction is fully explicit.
All right, great. Let's thank you.
Thank you.